Okay, so hi, my name is Sigalit. I'm a data researcher at SimilarWeb. I'm also working with Professor David Horn from Tel Aviv University from the School of Physics. So I will start with a short introduction about SimilarWeb and then go on describing quantum clustering, a clustering algorithm inspired by physics developed by Professor David Horn and Dr. Asaf Gottlieb. So SimilarWeb was founded in 2007. We are now more than 300 employees at 6 offices around the world. We provide estimates and valuable marketing and business intelligence insights for 60 million websites and 2 million mobile apps daily. Here you can see some of the matrices we provide. For example, for website, we provide traffic estimations. How much visit does a website have, and the distribution of these visits from the different traffic sources. For example, how many of these visits came from direct, from advertisement, from social media, and so on. So this information is used by thousands of businesses, especially by the marketeers department, in order to understand what's going on with our competitors and plan their online strategy accordingly. So in order to provide this information, we use various sources of data, and we process over 100 terabytes of raw data per day. So we are obviously a big data operation. And as such, we use various data mining techniques and machine learning algorithms, statistical algorithms. We develop some algorithms, customized algorithms, and integrate existing machine learning algorithms just for the products itself and for internal testings. So let's go on to the quantum clustering. But before diving into quantum clustering, let's give us a quick overview, simplified overview about what is clustering. So clustering is an unsupervised learning problem dealing with unlabeled data. Given a set of elements in some feature space, described in some feature space, we are trying to group together elements that are similar to each other in some sense. Of course, our ability to group together in a specific sense is strongly dependent by the features that describing the elements. So we usually have an idea or a desire of what the sense of grouping should be. However, we might discover unknown patterns and new structure in the data. Example from the industry of internet. So our elements here are internet user, and the features are the sites they served. For example, we have a male doctor here that served NCBI, if someone recognized the site. NCBI to read some medical article. He served Amazon and another medical site, and is a child school website. We have another a female doctor, 2 programmers, male and a female, a scientist, 2 children, male and a female, and a tennis player. Just a second. Okay. Please keep in mind that this is an unsupervised learning problem. So the identity of the user is unknown, but I'm leaving the identity just for the example, for the simplicity of the explanation. So a possible desire would be to group the users by the gender. However, given this specific feature space, we are more likely to be able to group the users by the fields of interest. So that's it for the general overview. So what is the motivation for quantum clustering? So there are already many clustering algorithms. Why do we need another one that it's a little bit maybe more complicated to most of us to understand? So on the left side, you can see a pretty easy clustering task that most of the algorithm will do just fine in case you give them the right number of clusters. On the other hand, you can see a pretty complex clustering task. Just I'm going back to that side. Here you can see that the data points are well separated in the feature space. This is why it's pretty easy for most algorithms. On the other hand, you can see very complex data. The data points are mixing together. The number of clusters is unknown a priori. This specific data belongs to each data point is a pixel in some piece of art made of different materials, and the feature space is the absorption, X-ray absorption energies. The initial dimension of the problem was 150. That means that each pixel was characterized by 146 possible absorption energies. And SVD, singular value decomposition, if you're data scientist, most of you probably know, SVD was applied in order to to reduce the dimension of the problem to the 5 most important components, principal components. So here you can see the quantum clustering process. Each data point is moving towards the direction of the cluster. Finally, they end up with a cluster that are strands, 3 separated strands in the feature space, and recognize the different materials in the data. So quantum clustering was able to identify the fact that there are 3 different types of material. It was also able to find through a very complex feature space the fact that there are 3 clusters. Its ability to find clusters that are not just a point cluster enables it to find structures and patterns in very complex feature space. So why is it important now? We are in the information era of big data. We have massive collection of data and strong presence of outliers. And we're looking for unknown structure and non-trivial patterns. So quantum clustering addresses these issues, and it is enabled now to implement on lots of data sets, thanks to distributed computing technologies that we just also saw a lecture about, one of them. So I know this is a little bit scary for maybe. So quantum clustering, this is the process of quantum clustering. I will give a brief explanation for each one of the steps. So we turn each data point into a Gaussian, center around the data points, and we end up with that sum. So the reason for that, actually we can look at our data as a sample of data. If we had much more data points in the space, and we would have built a density function that described the probability of finding a data point in the space, we hope that this sum would converge to that density function I just mentioned. Of course, you have to normalize it, but it's not important for the process. So the interpretation of this sum as a density function is important for the physical formulation. If it's a density function, you can plug it into the Schrödinger equation and find the potential. This is I'm speaking for the physicist here, and I see some. So we define the solution for the potential as the potential transform. This is what's important. You don't have to understand all the things that behind, but this is what's important. The potential is just a second derivative if it's one dimension, or the Laplacian for a multi-dimensional problem, divided by the density function itself. So single data point will turn into Gaussian, and then the Gaussian will turn into potential with that specific formulation. This is an harmonic potential or polynomial equation. And multi data points will turn into something much more complicated. Now we move each data point towards the direction of the minima of the potential, according to the potential surface. So why does it make sense? So the Laplacian modeled the divergence effect from the cluster center. The potential models the effects that binds points together from the same cluster. So essentially what we're doing, we are looking at the density function describing the data points in the space as originated from two different effects, divergence and attraction. We are looking for the attraction. So we are looking for the minima of the potential since this is where the divergence effect are its minimal. It is also pretty easy to understand mathematically. If we're looking for the minima of the potential, that means that we're looking we're looking for the minima of the second derivative and the maximum of the density function itself. This is essentially where there are slow changes in the density function, and the density itself is high. This is exactly the definition of attraction, and this is the cluster. Another important issue that I mentioned the example in the beginning, that SVD may be performed prior to clustering, and then the clustering is performed on the U matrix and V matrix of the SVD. This solves the fact that each feature may have different dimension type and a different scale. It also enables dimension reduction to those with the highest variance. Okay, so after we are familiar with the notation of quantum clustering, let's take the crab example. Okay, so the original data is crabs that each one of them is described by 4 features, a few dimensions of the crabs. SVD was applied to reduce the problem from 4 dimensions to the 2 most important principal components. So that means that we are supposed to see the data in where the data is much more distributed, and this is what we're seeing here. However, though this is the space where the data is much more is it with the highest distribution, we still cannot see what's going on here. Then we turn each data point, if you remember, we turn each data point into a Gaussian. And here is a topographic map of the sum of the Gaussian. So you still cannot see that there are 4 clusters. Now here the 4 clusters are labeled with color and shape. But you can still not see anything. However, when we're using the potential transform, you are able to see 4 clusters. Here you can see the potential transform in the higher dimension. This is actually a result of different sigma. This is the only parameter that quantum clustering requires. So you can see this is a topographic map of the potential. And this, the fact that there are 4 different groups in the data was stable among a range of sigmas. That makes us confident with the result of 4 clusters. So quantum clustering, a summary. Quantum clustering has a built-in capability to handle outliers in the divergence part. There's in the sense that there is no need for additional parameter or process to handle the outliers. Actually, outliers may just result in isolated cluster with just very little data points, very small amount of data points. There is no effect on the amount of significant cluster. The outliers does not affect the amount of significant clusters. The cluster may be a line or other shape and not necessarily a point, as in the example I showed in the beginning, and therefore is able to find structures and patterns in very complicated feature space. There is no need to predefine the amount of clusters, which is pretty important and also always a question when you're handling clustering algorithms. There exists approximated quantum clustering for improving the time complexity. And since all we have to do is to calculate the potential and its derivative, its gradient for every data point, we can just do it in separated a different machine and implement it in a distributed manner. It performed exceptionally in exposing hidden patterns of data structure from wide range of fields. I mentioned here some of them: finance, online marketing, experimental physics, and speech recognition, biological data, which is connected to the lecture in the beginning. So to sum it up, a final word, clustering is a challenge that challenge to many fields and many companies, many questions. And here, through different approach, quantum physics and quantum mechanics, quantum clustering addresses many issues that are problematic in clustering and improve results. That's it. And if you're more interesting, you can just surf to Professor David Horn website. You can find the articles and the papers and the implementation. The implementation there is in Java, but I have implemented it in Python, and if you like, you can approach later. Okay, thank you.